Okay, so in ionic equations, you're going to keep weak acids together and you will separate strong acids. All right, what is an Arrhenius base? It releases OH minus in water. And what would be attached to the OH? Like what does it come with? Metal ion. So for example, LiOH, CaOH2, etc. Yes? Or ammonium, yes. Let's look at a reaction between an acid and a base. What is a reaction between an acid and a base called? Reaction, we have neutralization. So let's start by taking a strong acid, HCl, and reacting it with a strong base, LiOH. And I would like you to please predict the products of that reaction. Okay, who are our products? Who are the products? Who are the products? Water, H2O. Who's our other product? Lithium chloride, LiCl. What are our states? Liquid and aqueous. So we're going to write a complete ionic equation. This is our formula equation. What is our complete ionic equation, our CIE? H plus Cl minus plus Li plus OH minus, Li needs a plus sign, goes to H2O. I'm not separating them to H and OH. You're right, I'm not. Good. That stays together. Okay, and then our other products are Li plus Cl minus aqueous. Everything's aqueous except for the water, yes? Hooray! Now, what would you do if you wanted to write the net ionic equation? H plus OH minus gives H2O. And that's going to be the complete ionic equation for any strong acid, strong base. Okay? All right. Let us try, okay. H2CO3 plus KOH. What's one of our products? H2O. What's our other product? Potassium carbonate formula is K what? Okay, because even though when it dissociates, really mainly it's one hydrogen that's coming off more than the other. Okay, you will get a second dissociation. Yes, so this is the first dissociation. This is the second dissociation. Could you find me a Ka value for H2CO3, please? Go look on your chart, your pink sheet. 1.5 times 10 to the -2. That sounds really large. (4.3 times 10 to the -7. Okay, good. 4.3 times 10 to the -7. So is that a big K value or a small K value? That's pretty small. So that's what tells you that H2CO3 is mostly together. Yes? Now let's take a look at our second dissociation. What is our Ka value for our second dissociation? (5.6 times 10 to the -11. How many times smaller is that approximately? 4 times smaller? No, it's not 4 times smaller. 10 to the 4 times smaller. And what's 10 to the 4? 10,000 times smaller. This is Ka1, Ka2. Ka2 is 10,000 times smaller than Ka1. So how important is Ka2 compared to Ka1? Not very. So if we were to start doing, some ice tables, some rice tables with some of these things, we would just look at the first dissociation and ignore the second one because the second one is unimportant. So when we get to the rice tables, we will only consider the first dissociation. And we'll just ignore the second one because we're like, it doesn't matter. It's just so insignificant. This should be a 2 minus. Oh, hang on. So let's go back. Now that we've done our first dissociation, our second dissociation, we're going to go back to our original equation, okay, because we were reacting the H2CO3 with the KOH. Water is a liquid, right? That was sad. Oops. Water is a liquid, K2CO3 is aqueous. Is this reaction balanced? No, there are two ways of balancing these reactions to make it fast and easy. Method number one is to write H2O as HOH and balance the H and the OH separately. Yes? My preferred way, because then I don't have to write it as HOH, is that I need the same number of hydrogens. So the number of H plus is going to equal the number of OH minus, which is going to equal the number of waters made. So if I look at this and I say I have 2H plus, that means how many hydroxide do I need to neutralize that? 2. Put a 2 there. How many water will it make if I react 2 hydrogens with 2 hydroxides? 2. Okay? But like I said, the other way of doing it, if you ever get stumped, is to write it out as HOH and balance the OH separately from the H. Okay, and that will also work quite nicely. So this is now a balanced reaction. So if you're wondering what happened to the other H, that's where it went. Okay. Now that we have that, let's see if I can grab it. And we're going to then take it and uh-oh, what's happening? Ah, it's going crazy on me. It's okay. It's okay. Here we go. All right. We're going to take this and you're going to write your complete ionic equation and your net ionic equation, please. Try that. Mm-hmm. Yes, I'll go back to that once we finish this. If I don't, remind me. What do you guys think? Why is the H2CO3 all together? So let's take a look at H2CO3, yes? And let's do a rice table for it, yes? That's its dissociation. That's how much it dissociates. I'll stop writing so fast. I'll give you guys a minute to get caught up. So let's say that we have 0.1 molar H2CO3. If we have 0.1 molar H2CO3, that tells us that we took 0.1 mole of the H2CO3 and we put it into 1 liter, yes? So what would be the initial concentration of the H2CO3? 0.1 molar. That's how much we put into solution. If you're not talking chemistry, you're not talking. Okay? Now, initially when I throw that acid in there, how much has dissociated? 0, right? Because in that instant when I throw it in, it has not dissociated. It will then proceed to dissociate, but initially none is dissociated. So if I wanted you to figure out how much had dissociated, could you do that? What would you do? We know the Ka value, so we know the K value. Oh, plus minus, what are we plussing? We're plussing X because we don't know how much, right? And what are we doing on the reactant side? Minus X because that's dissociating. Okay, so we have 0.1 minus X, and we have X, and we have X. Is good? Okay. What would we do now? We've drawn our rice table. What is the step that comes after a rice table? The KEQ expression. In this case, we're going to call it a Ka expression. Okay, so Ka is equal to, and what's going to go on the top? Concentration of H plus times concentration of HCO3 minus over what? H2CO3. So now we have the expression. So you draw the Rice table first. You write the KEQ expression second. What do you do third? You replace everything. You plug in stuff. Do we know a Ka value? Oh, what happened? Yes, we do. So let's plug it in. 4.3 times 10 to the minus 7. 4.3 times 10 to the minus 7 is equal to x squared over 0.1 minus x. Do you guys love solving quadratic equations? No, I don't either. Wouldn't it be nice if we could simplify this? Now, remember, what was our Ka value? 4.3 times 10 to the minus 7. So how much is actually dissociating? Not much. X will be very small. Because the Ka value is small. So what we're going to do is we're going to simplify our lives, and we are going to say assume X is much, much smaller than 0.1 molar. Does that make sense? Okay, you have to write that assumption. If you do not write that assumption, then you will lose a half a mark. Okay? Okay, so you have to write the assumption or you will lose half a mark. But that's going to make our life nice and easy, yes, because now we can write 4.3 times 10 to the negative 7 is equal to x squared over 0.1. Do we like that better? Nathan, you look a bit puzzled. You're good? Okay. How are we doing on this side of the room? You guys are good? Okay. Now we're going to solve this. So x squared then is equal to, well, 0.1 times 4.3 is 4.3 times 10 to the minus 8. And now we're going to solve by taking the square root of the whole thing. (4.3e negative 8 square root 2.07 times 10 to the negative 4. We'll get to that later. Now, hold on, because I'm going to rewrite this just in standard notation so you can see how small it actually is compared to 0.1. Yes? This is actually 0.000207. So was it okay to make that assumption? Yes. In regular chemistry 12, you can always make that assumption. They assume that you don't know how to take a quadratic. You don't have to do the quadratic, okay? However, you should, in AP, check your assumption and see if it actually is smaller. The smaller your initial concentration is, the more likely it is that the X will become significant. The larger the Ka value is, the more likely it is that the X will become significant. But if you have a high starting concentration, and by high, that could be like 0.1. 0.1 is considered a high concentration because we really kind of max out in the tens, okay? So as long as the concentration is high and the Ka is relatively small, you are good to go on making that assumption. Yes? It's possible. I don't think they're going to make you because it's time consuming and it's a waste. It's kind of a waste of time. So my guess is that they will never make you do it. Okay? University, different story. But I think on the AP exam, I don't think they're interested in having you grind through the quadratic formula. Yes? Oh, dang. Okay. 4.3 E8 negative root 2.7 times 07 times 10 to the negative 4. Let me try squaring that. 4.3 times 10 to the negative 8. What? What are you guys getting? Show me what you did. No, you didn't. You're taking times n. Trust me. Trust me. You didn't have me last year going, oh no, you can't do that. You remember me freaking out about the exponent button last year? And if Matthew can't show you, get someone else to show you, or I'll come back again. Yes. You will make this assumption when you would have to otherwise do a quadratic equation. Okay? Yes. Make this assumption if and only if you would otherwise have to do a quadratic equation calculation. Is good? One. We're going to check our assumption. Okay, and we're going to take 0.1 and we're going to, did you get it sorted there, Rigel? Cool, excellent, okay. So we're going to subtract that from 0.1 and we get 0.9979. Now let's assume that we had some reasonable number of sig figs, okay? Let's make it, oh my gosh, let's make it 2 sig figs here, okay? So it's going to make a difference. Like if you had 3 sig figs, then maybe it would start becoming significant. Oh no, did I do that wrong? No, we're okay. Oh no, it wouldn't even be significant even if it were 3 sig figs because I forgot a 0 here. It's 0.09979. So I could even have 3 sig figs and that would still round up to 0.1. Yes? So you can see that our assumption is okay, right? Because that would round to 0.100. Okay? Now, let's just make a note here. The assumption is most likely to be valid if what is small and what is big. If Ka is small, because that means only a little dissociated, and if what is big, concentration of the acid is big, because that means that your small amount is going to be small compared to the big amount. Yes? I'm not going to write that down because that's just sounds silly, okay? The small amount is small compared to the big amount. So now going back to our whole thing here, because we were getting to your question, Adriana, by a roundabout long route, okay? So shall we zip back up here for a moment? So if we look, we've got this concentration is the concentration of hydrogen, so 0.0002. Okay, we're not going to worry about sig figs. So if it is only a little tiny bit dissociated, why are we writing the H2CO3 together? Because it's mostly together. Yes? And we've proved that by doing the math. All weak acids will be mostly together. And if anyone wants me to print out these notes at the end, I can definitely do that. Okay, let me know. So when it comes to writing neutralization reactions, if it's a strong acid, you split the ions apart. If it's a weak acid, you keep the ions together. So is that good? We're feeling all right about that? Okay. So we've talked about Bronsted, or no, we've talked about areneous acid. Actually, I'm going to get you to do one more because, yes, sorry. If it's a big Ka and your concentration is small, you might have to do the quadratic. Like I said earlier, if I were betting, you will not have to do it for AP because I don't think they want you to waste your time grinding through the quadratic formula. And certainly in regular chemistry, so the exams you're writing for my class, you will not need to use that. You will not need to use the quadratic. Now, let's look at a case though where you would not make that assumption, but you won't make it because you wouldn't have to use a quadratic anyway. Okay, so let's look at a case like that. Okay. When, spelled W-E-N. Oh my gosh. Okay. When the change in concentration is an actual number and not X. Yes. Uh-huh. No, no. If it's a weak acid, keep it together. If it's a strong acid, split it apart. That's all you need to know. Yep. You do not have to prove anything. Okay? They won't. Okay, we're not to make an assumption. When the change in concentration, that's our C in our RICE table, is an actual number, not an X. Because if you don't have an X, you won't end up with a quadratic equation. No X, no quadratic. Yeah? Simple. Should we do an example like that? Okay. The hydrogen ion concentration in a, again, we're going to use simple concentrations, 0.100 molar solution of acetic acid is, what's a good concentration? I don't know. Hold on, let me think hard. 4.2 times 10 to the minus 5 molar. Sure, that sounds good. Let's hope this works. Okay. Actually, you know what I'm going to do? I'm going to do minus 4. There we go. No, yes, no. 3. There we go. 3. Okay. I don't know if this is going to work out okay, but we're going to go with it, okay? So now, what is O? Not of acetic acid, of an unknown acid. That's why. Is 4.2 times 10 to the minus 3. This is why I was thinking I'm going to have problems, because I'm like, I can't make it equal. Of an unknown acid. It's not acetic acid, it is an unknown acid. And we want to find its Ka value. What is its Ka? If you think you can do this without any prompting, give it a try. Do you want to give it a try? Give it a try. See if you can do it. Yes. That is always, when we are given the concentration of an acid, it will always be the initial concentration, because you have to do calculations to find out what it is after dissociation, whereas you know how many moles you put into how many liters. So the given concentration of an acid will always be the, oh, let's write this down. Yes, because remember, a second dissociation is insignificant compared to a first dissociation. So we can ignore, we can just assume it's a 1-to-1 ratio. It's what? The weak acid, yes. If it has a Ka, it is a weak acid, yes. 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 So what should we write for our acid? You know what you can call it? You can call it HA. HA for acid. That's what we often call them, or HX sometimes. Yeah, it'll be A minus. So if you've got that, you want to think, what tool will I be using? We have been given an initial concentration. Yeah. No. The hydrogen ion in 0.1 molar HA is 4.2 times 10 to the minus 3. So the hydrogen ion concentration yes? You guys don't know how to take notes, do you? You're all scribbling things in weird places. Like honestly, when you take notes, get in the habit of like writing them on a real piece of paper and doing them like top to bottom, left to right, because then you'll be able to refer back to them. Yes? I babied you too much because you're all really like, oh, I'm just writing everything everywhere on a scrap piece of paper, la la la. Yeah. All kinds of weird stuff in there. Do we feel good about the I line of our rice table? Yes? Am I going to be putting X in the change? No. What do I actually know? I know the change because I know that my equilibrium concentration of hydrogen is 4.2 times 10 to the minus 3. I'm actually going to write it as 0.0042 just because I like to see it. I like to see where my decimal is. You can write it as 4.2 times 10 to the minus 3. I just like to see where the decimal is. So if you know the initial and you know the equilibrium, what do you know? You know the change. Sometimes people get a little confused. They'll see that the hydrogen ion concentration is 4.2 times 10 to the minus 3, and they'll think that's the initial. When you initially put the acid in, how much has dissociated into hydrogen? None. Always the initial amount dissociated is 0. Mm-hmm. Okay, the question is, do we always assume that the coefficients are 1, 1, and 1? And the answer is yes, we do, because even here in that previous example, you can see we have 2 hydrogens. But when we're doing a rice table, we only take off 1 hydrogen. And let's go back again and see why. Here is our first dissociation in yellow. First dissociation. That's that first hydrogen coming off. Its Ka value is 10 to the minus 7. Our second dissociation, that is the second hydrogen coming off after one has already come off. The second dissociation is 10 to the minus 11, which is 10,000 times smaller. So how significant is the second one compared to the first? It really isn't. Plus, listen to this. Look at this hydrogen here. We already have some hydrogen present. So what is that hydrogen going to do to this equilibrium? This concentration is higher, so it's going to shift it that way, so it becomes even less important because we already have some hydrogen present. So, rule of thumb when you're doing a rice table, only dissociate the first hydrogen of a polyprotic acid. Polyprotic meaning having more than one hydrogen, proton, hydrogen. Do you remember that from the stuff? Okay. So when you're doing a rice table, only dissociate 1 hydrogen. However, let's take a look up here while we're here, because you'll notice that what happened here? Both of our hydrogens became part of water, yes? And the reason for that is that I need someone to come and be H2CO3. I need a couple people. Come up and be H2CO3. And I need a couple people to come up and be, yes, come. Yes. And I need a couple of people to be LiOH. I need a couple of people to be OH. Okay, OH. Okay, here. These are your hydrogens. These are your hydrogens. Okay, you stand there. Okay, now, Nathan is hydroxide, and Daniel CO3. Now, in water, I'm going to be water, okay? So I'll be like, oh, here, I'll take one of those and I'll give it back because, most of the time it's like this, and every once in a while I'll be like, oh, no, don't do that. Right? So every once in a while, these are dissociating, they're giving to water their proton, but mostly they are associated because what kind of acids are they? They are weak. But what kind of base are these guys? Strong. Now, we're getting more into the Bronsted-Lowry definition of an acid and a base, right? When I am taking a hydrogen, I have been a proton acceptor and you've been a proton donor. Donating, accepting. Donating, accepting. What is he? Is he a Bronsted-Lowry acid or a Bronsted-Lowry base? He's a Bronsted-Lowry acid, and in accepting a proton, water, I am a Bronsted-Lowry base. Okay? We'll get more into Bronsted-Lowry tomorrow. Okay? But these guys here are very strong Bronsted-Lowry bases. Okay, OH minus. So what are they good at doing if they're strong? They're really good at taking those protons. Actually, I need 2 more hydroxides. Can I get 2 more people, please? 2 more people. Volunteer now. Yes, thank you. 1 more. Do it. Thank you. Okay. Why are you guys so shy? Goodness gracious. Thank you very much. All right. Now, I have hydroxide. Poor Aaron's being shoved out because we have hardly any room up here at the front. You guys are hydroxide. You are going to go and you are going to... Yes, it is. Do you see what happened? They're CO3 2- now, yes? Because the strong base was there to rip the hydrogens off. That's different from when the H2CO3 is just hanging out in water. When it's hanging out in water, water is not like really keen to take that hydrogen. It's just like every once in a while it'll take and it'll give it back. How about you guys? What are you going to do with that? Try and take it back from me. Right? They cannot take it back. All right, thank you guys so much. Thank you. We will, yes. Yes. Oh, of course, yes. Yes. Okay. So did we like that? Did that make sense? So you can see that only this one is important when we're only in water. Oh. This one here is important. This one here is insignificant. Yes? But when we put a strong base, the strong base will rip the hydrogens right off of those weak acids. Okay? And you wanted to know how we know which ones are the strong bases. Which metal hydroxides are the strong bases? Let's go to the periodic table. The alkali metals. It's a big B. Big B for base. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and then calcium, strontium, barium. Yes? The other way to remember it, if you don't like that, if you don't like drawing the big B, is maybe this is not so useful anymore because you guys don't watch very much network TV. Do you guys know the station CBS? Yes? Look, calcium, strontium, barium, CBS. CBS. Except for CSB, but CBS. And then the alkalis. Okay? Is good? Okay, excellent. Now, let's figure out what we're going to have you guys do for homework. I'm going to need to borrow someone's book because I don't have mine currently. I'm going to have you do, I sort of skipped ahead. Okay, page 96. Page 96. But you're not going to do everything. You are going to do A for all of them. And you are going to, for part B, you're going to find H plus for the strong acids. For the weak acids, and we're only going to go up to number 6. Only up to number 6, and we will find concentration of OH minus for strong bases. Have we got that? It's all going to be on Teams, but I'll make it big, so if you want to take a picture, you can take a picture. Okay. And if you have extra time, what should you be working on? AP thermodynamics, because how often does AP thermodynamics show up? Every flipping year. If you're feeling really good about it, you should be like, but if you're feeling like, I could use a little more practice, if you've done these, then you can go ahead and do the other ones. Okay, only up to number 6 here, because after that they start getting a little complicated. I'm done with the book. Thank you so much.